get started with today's lecture. So, as I mentioned, we'll be using these two books in addition to the books that we were using. So, Putterman was the book that I was using so far. Now I'll be using Dynamic Programming and Optimal Control Volume 1 and 2 by Bertsikis. And the reason why I need to use multiple books is that some books go too much into general results and some books are into somewhat specific results, and therefore it makes sense to mix the results from multiple books so that I can cover the easier parts in the class. And so if you want to look into the more difficult things, then you can refer to the book. So we were talking about value iteration algorithm in the previous class. So Vk plus 1 equals to Tvk, where Tv of I equals to min of summation Viju Ciuj plus alpha Vj. This summation is over all j. For brevity, I might have to introduce some notations. So I'm also going to write it as follows. I'm just going to write it in this fashion because I don't want to write this big expression. So sometimes I'm going to write it in that way. And I'm also going to introduce a few notations. So C mu, so for a policy mu, C mu equals to summation and P mu V you can also think of it as a matrix P mu getting multiplied by a vector V. Okay, so these are the two notations I am going to be using in today's class. So this can be viewed as a matrix, this can be viewed as a vector. And this is the ith component of that vector. This can be viewed as a vector as well. Sorry, this is a scalar, but you can stack. Sorry,
V of I.
V of I is a scalar. Yeah. That's right, but this is P mu V of I. Okay, P mu V is like it's a function, but you can also view it as a vector. That's what I was mentioning here. Okay, so you can think of P mu as a matrix and V as a vector. So that's the benefit of being in finite state, finite action setting, where some of these things are as easy as matrix multiplication. When we go to continuous state setting, then we'll have to be a bit more careful because these would become operators. Yes?
So in the same operation, you also do UI.
Oh yeah, of course. Thank you. That's right. Thank you. So this u in the cost function will also be mu I, because that's the action we are taking. Please make a correction here. Any other question? Okay. So there are a few things we need to cover today. It's going to be somewhat intense class because we are going to talk a lot about the convergence of value iteration algorithms, and then we'll talk about average cost and stochastic shortest path problems or total cost problems. Right, so let's get into it. So the first thing that so if you recall from contraction mapping theorem, let me just recall it here. You don't need to write it because this is something that's there in your notes already. So fx1 minus f of x2 is less than equal to alpha times x1 minus x2. Then xk plus 1 equals to fxk converges to x star, which is unique fixed point of f. Okay, so this is the Banach contraction mapping theorem. And remember, one of the comment that I had made in the previous lecture was sometimes the function f is given, right? We can't really do much about the function f, but we need to identify a norm. We need to identify a norm over which this particular function is going to be a contraction. So now the question comes back to us. This operator t is given to us, this function t is given to us. All I need to do is figure out what is the norm under which this t is a contraction. Okay, so that's our problem statement right now. And I'm going to propose that let's look at the soup norm over the space of value functions. So remember, the value functions can also be viewed as a vector, and I'm going to endow this vector space with the soup norm or infinity norm or max norm, whatever way you want to call it. And all I have to prove is tv1 minus tv2 infinity norm is less than equal to some number alpha. So it will turn out that this alpha is the same as this alpha times v1 minus v2. So this is something that we need to prove. Oh, this also has to be infinity norm. So how do we go about proving this result? Let's write this down. So I have, let me write A1 star equals to argmin let's write AI star U in UI maybe I should call it UI star. And V1, let's do it for V1. So I need to look at this particular expression. So this is summation Pij UI star this summation is over all j, Ci ui star j plus alpha v1j minus min of expected value of C plus alpha v2. Okay, this is what I need to bound. What should I do? How do I remove this min? This min is the one that's creating the problem. So here I have been able to replace it with ui star, but here I have a min, and that's creating a problem.
Using like because it's me, it is equal or less. It is less
Right.
or equal to I.
Yeah.
With ui.
So this min is over all u, right? So can I say something like this? So this min, so actually maybe I need to make it V2, right? So if I make this V2, then this term will be an upper bound on the min term. Okay, so let me try something. Okay, so I have min over u expected value of C plus alpha v1 minus min over u C plus alpha v2. I'm going to let ui star be the argmin when you have v2 here, right? So I can just replace this min by ui star. Now this is minimum over all possible actions. So in particular, if I evaluate this at ui star, so I have pij ui star C plus alpha v1 minus summation this is over all j. Does this inequality make sense? So I've just replaced the whatever the minimum u is going to be, because this is the minimum value, I'm just going to replace it with some other ui star which may not be minimum, so therefore the value of this term is going to increase. Right? That makes sense? Okay. Now this just seems to be a regular summation, right? So difference of one term minus summation of some other term. So now I can C minus C, what does that give me? 0. Alpha will come out and I'll have V1 minus V2. V1j minus V2j. Any questions so far? Any questions so far? Does all of this make sense? So the C term is going to cancel, C minus C is going to cancel, alpha is going to go out because it's a common multiple both in both sides, and then I'll just be left with V1j minus V2j. What is V1 minus V2 upper bounded by? V1 minus V2 infinity, right? So this is v1j minus v2j, which is upper bounded, v1 minus v2 infinity what is this equal to? I have a transition matrix and I'm summing it over all the entire columns, right? So for every I am summing it over entire columns, and that's going to sum to 1, right? Because it's a transition probability. So it has to transition to some state j in the future, right? So if I sum it over all j, it's going to be equal to 1. So I get alpha v1 minus v2 infinity. Sorry? This transition thing? Okay, so remember that Piju is the probability that the next state it plus 1 equals to j, given it equals to I and ut equals to u. Right? So that's the idea. And what's a property of a probability measure? So if I sum it all up over j, this has to sum to 1. That's the requirement on probability measure. That each of these has to be non-negative and it has to sum to 1. So that's the property I'm using here. The other property that I'm also using here, going from this equality to inequality here, is the fact that these are all non-negative. So I can replace it by v1 minus v2 infinity, and I can have the less than equal to sign here. If one of these terms could be negative, then this operation would not be valid. But because all of these are non-negative, this operation is valid. Yes?
I have a question on the first step. So what I'm thinking is like, assuming there are two equations, A is less than B, C is less than D. So taking the minus on the two sides for the second equation, for example, like minus C will be larger than minus D. They use sum on each side. But at this moment, it is not a like uniform relationship. So for the first step.
This side?
Yeah. So
Yeah.
you are adding, probably you are adding A minus C and B minus D, right?
Right.
But A is larger than B, minus C is smaller than D, minus D. So it's not the same sign on each side.
So I have A minus B.
Oh,
No.
A is less than B.
A is less than equal to B.
C is less than D.
C is less than equal to D.
Yeah,
But I am not using C less than equal to D. In my case, C is equal to D. So I'm just replacing this min by the actual value ui star. Okay, so this ui star is essentially the same as this. Remember, ui star is the argument, right? So I'm not replacing it with something that is less than equal to D. It's actually equal to D. Right? Very good point, but I'm making sure that this term is the same and only this term increases. This term increases in value. Any other question? Yes, please.
So there should be, we're looking at the norm of the difference, right?
That's right.
Which isn't written, but.
It's not written, but what I'll do is, suppose I flip it, okay? So I do V2 minus V1. In that case, I will go through the same set of equations, except that instead of ui star being defined for V2, I'll define it for V1, and I'll end up getting the same inequality. So it means that this, in absolute value, is less than equal to this. And then if I take the max over all I on this side, it's also less than equal to this, because this one doesn't depend on I at all. This is a constant, right? This is a constant, it doesn't depend on I. and I can go through the same argument again, and I'll get that. I'll get this particular result. Yes, please. Here? This one? This one, because this is the minimum value. So let's do it without the absolute value. So this is the minimum value. I'm going to replace it with UI star. I don't know whether UI star is optimal for this or not. Okay. So what I'm using is the fact that I have a function f of x min over all x. This is less than equal to f of x bar, right? By default, I pick any x bar. This statement will always hold true because this is the minimum value. Second term is equal. That's what the question was. Because I'm picking UI star as the argument of this term with V2. There was a question there, right?
I was going to say it right. Are you picking is UI star just an arbitrary?
It's not quite an arbitrary action. It's an argument of this statement.
Okay.
So it's not arbitrary at all. It's a very specific action which is optimal for this particular equation. Just the second one, yeah. Just the second one, not the first one. It's arbitrary for the first one, but not arbitrary for the second one. Yeah. It's a very common trick, and that's what I wanted to show you. This is a very common trick in MDPs, and so I just wanted to show you how this trick works. Any other question? Yes, please.
I'm sorry, you said we're just looking at each I individually.
Right.
To get the soup norm.
So yeah, so initially I'm looking at it for a specific I. Okay, so this is all for a specific I. And I get this inequality, then I'm going to flip it. Okay, so this term will come here, this term will come here. I'm going to go through the same argument in order to get to this particular inequality. So it's true for every I with an absolute value. And then I'm going to take max over all I. Yes, please. Right now, we are not talking about uniqueness of UI star. So if you have multiple arguments, you just pick one of them. It doesn't matter which one you pick. Yes.
What's the difference between the first and the second term, because they apparently the expression was the similar, just V1 and V2.
Right. So depending on what V1 and V2 is, the argument is going to be quite different. Right. So remember, these two V1 and V2 could be anything. So it could be like, so if you think about a value function space, I can pick V1 to be here and V2 to be here. It could be very far apart. Right. So the argument is going to be quite different for different values of V. Any other question? Okay. So I guess I have convinced you that this statement holds true. So for a given operator T, which is called a Bellman operator, for a given Bellman operator T, we've been able to identify a norm, infinity norm, under which T is a contraction. Consequently, recursive application of T is going to get me to a fixed point of T. Okay. What is that fixed point? I don't even know what the properties of that fixed point is going to look like. So let's look into that. Can I erase this side? We are going through this exercise in great detail for the discounted problem, but we will not go through it for the average and the total cost problems. I actually went through it in my previous version of the reinforcement learning class, so it's there in the spring 2020 videos. But I spent a whole class just deriving these equations, so I don't want to do that in this class. So I'll just show you how it works for the discounted cost case, and then I'll give you the results for the average cost and the total cost. Okay. So let's look at it. So I have this value iteration. So I have proved T is a contraction. So Vk converges to some V bar, which is a fixed point of T. So T V bar equals to V bar. What does V bar has to do with the original problem? So I want to remind you the original problem was I want to minimize J of mu, where mu is in the class of all Markov deterministic policies. And remember, it's a dynamic problem. So my mu star, which is the optimal solution, would have a sequence of Markov deterministic policies, mu1 star, mu2 star, all the way up to mu infinity. I mean, not mu infinity star, but there will be a sequence of policies which will be the optimal policy for this particular J. Now the question is, what does this V bar that we converge to, what does it have to do with this J mu that we talked about? So I'm going to claim so remember, J mu star is a function of initial state I0, and my claim is this V bar I0 equals to J mu star I0. So whatever is the optimal solution to this problem, if you start with I0 and you apply the optimal policy throughout the horizon, through the end of the horizon, so which is infinite horizon setting, what you get is V bar I0, which is a fixed point of this. So in fact, V bar is the optimal value. So we call it value function, optimal value function, the optimal value function for the discounted MDP. Yes.
So previously when you defined J, there was an expectation.
Yes.
And I always assumed that expectation was over I0, but now you're saying it's conditional on I0?
It's conditional on I0. You can generally do the expectation over I0 as well. But in that case, you will just have a scalar V. So V would also be a function of the initial distribution in that case.
But I guess typically when you think of J, you think about it as condition on I0, or we just want to think about it as?
It depends on different papers.
Okay.
Or different references. So some people assume that there is an initial distribution and then they write the rest of the paper assuming an initial distribution. But in the context of but most of the authors, or rather the initial papers that were written on reinforcement learning, assumes that there is a specific I0, and that I0 could be arbitrary. It could be from any set of initial conditions, in which case V becomes a function of I0. Okay, so the question was whether this I0 is fixed, I0 is variable, or there is a distribution over I0. And it really depends on the setting and the problem statement and so on. In the context of LLM, when they are training large language models, they tend to assume that there is an initial distribution over the queries, right? So queries, whatever you ask, whatever your prompt is, that's I0. And then it goes through coming up with the response. So in the context of large language models, typically there is a distribution over I0. But for the purpose of this class, I'm going to assume that you can pick any initial state and then you can start running the MDP from that particular initial state. Any other question? Okay. So these are the claims that I'm making, and I need to establish these claims. So let's get to it. Okay. So I'm going to make the following claim. So if, let me write it as theorem. If V is less than equal to TV, so V is a vector. If every element of that vector is less than equal to every element of TV vector, then V is less than equal to V star. If V is greater than equal to TV, then V is greater than equal to V star. If V equals to TV, then V is equal to V star. So V is a vector. I applied this transformation T, I applied this Bellman operator T onto V, and I realized that every element of V is less than equal to TV. Then in that case, every element of V is also going to be less than equal to V star. I did the same thing, so every element of V is greater than equal to TV, then V is greater than equal to V star. So by corollary of these two results, if V equals to TV, then V equals to V star. Okay. So the third statement is obvious if the first two statements are true.
Are we considering the discounted?
Discounted. This is all discounted. Yeah, this is all discounted. So alpha is the discount factor. Yeah. Okay. So how do we go about proving this? So I know that V is less than equal to TV. So I know that V is less than equal to min U expected value of C plus alpha V. So this is min over all possible actions. So this must be less than equal to C mu 1 plus alpha P mu 1 V. Because, mu 1 star. This is the optimal solution. So this is the optimal solution. Okay, so V is less than equal to the minimum value of U of this particular term. So I'm going to replace this mu with U with mu I, mu 1 star I. So I get this less than equal to sign because this is minimum, this is a very specific action that I'm taking. Now this V, so I have a V here, this is less than equal to C mu 1 star plus alpha P mu 1 star C mu 2 plus alpha Yes.
Should the subscript 1 refers to time 1?
Yeah, this 1 refers to this mu1 star here. This is the optimal policy at time 1. Yeah. Then I'm picking optimal policy at time 2, then I'll pick the optimal policy at time 3 and so on. I can keep going on and on. What do I get? This is less than equal to C mu1 star plus alpha P mu1 star C mu2 star plus alpha square and it turns out that this is exactly equal to J mu star. Which is by definition equal to V star. Okay. I want to do a pictorial representation. So this is my V star. I picked a value function V here, and TV is going to be somewhere here. Okay, so V is less than equal to TV, then V must be less than equal to V star as well, right? That's what the first statement is saying. So I have a V star, I have a value function, I pick an arbitrary value function V, and I applied the Bellman operator. I am going to move closer to V star once I apply the Bellman operator. So this TV is going to be closer to V star because of the contraction property. If V is less than equal to TV, then V must be less than equal to V star as well. Okay, and that's what we have proved. I can do the same thing for the opposite direction as well. Okay, so if I flip this particular result, my V star is here, V is greater than equal to TV, so V is greater than equal to TV, in which case V star will also be less than equal to V. That's the second result. Okay, proven in a somewhat similar fashion. And that leads us to the third result. Now, how many fixed point T has? Remember, T is a contraction operator, right? We just proved that T is a contraction operator. So T has only one fixed point in the entire space of value function. And that fixed point turns out to be V star because of this result. Okay. So at least in theory, I apply the value iteration algorithm and I converge to V star. So this V bar is actually the unique fixed point of T, and the unique fixed point of T turns out to be equal to V star. So I have been able to compute V star. Now the question is, what's the optimal policy, right? So there were two questions we wanted to know. First one is whether a minimum exists, and the second one is how do we compute that minimum, right? So we didn't talk about whether a minimum exists or not, but again, something that can be proven using somewhat, it's a laborious argument, but not too difficult to understand. So minimum exists. That part is easy to prove. We've been able to come up with an algorithm to compute V star. Now the question is, what is an optimal policy? So if there are no questions on this, I'm going to erase this side of the board. Okay. and I'm going to claim another result. I'm going to define mu star I equals to argmin u in ui c plus alpha v star. So I pick this fixed point of t. So I run this value iteration algorithm on my computer. I get a v star. It converges to some v star. I pick that v star, plug it in here, do the argmin operation, and get a policy, a deterministic policy mu star. And then how about this? I make it a vector. So I define my overall policy mu star equals to mu star, mu star, mu star, mu star. So this is known as a stationary policy. It's a stationary policy because it doesn't depend on time. Okay. This policy was time dependent, by the way. I had mu1 star, mu2 star, mu3 star, and so on. So each optimal policy was different. But now I'm picking a policy where I'm not changing the policy with time. My policy is the same. And the way I computed this policy is through this argmin operation here. And it turns out that j of this mu star is equal to v star. This implies mu star is optimal. Yes?
Expectation is I dependent.
This expectation is I dependent, this set is I dependent.
So how do we know which I to use for the next line?
So you will observe the state, right? So you know what the current state is, that's your I, and then you apply the mu I star and transition to the next state. So at every point of time, you observe IT, and then you apply mu star IT, and then you get IT plus 1, and then you apply mu star IT plus 1. But the point is, once you compute mu star, you just store it in the memory, and then you keep executing according to that particular memory, according to that particular mu star. So if you look at the routers that we have in this room, they've computed a mu star when the router was being designed by some engineer in Silicon Valley or wherever. I think these are Cisco routers, so they must have been designed in Silicon Valley, in San Jose. That's where Cisco is headquartered. Somebody, and maybe this router is 10 years old, I don't know, but maybe this router is 10 years old. So this mu star was designed 10 years ago. It's stored in the router's memory, and the router is just executing that mu star again and again, again and again. It doesn't have to recompute mu star ever again. Okay. So it was designed once, and then every time it looks at a state, it executes mu star IT, looks at the next state, executes mu star IT plus 1, and so on and so forth. Same thing with this air conditioning system. So I don't know if you know, but the air conditioning system is tuned once in the summer and once in the winter, and that's pretty much it. So somebody on 1st of April must have tuned the air conditioning system of this building. Tuning means picking a mu star for this particular building, whatever is the optimal for this particular building. And then they look at the temperature of each room. That's your IT. So it's a 70 or 80 dimensional IT. So there are this room has one temperature sensor in the back, and every room, every classroom within this building, every office within this building will have one temperature sensor. So we'll have the IT, which is like 70 or 80 temperature readings of 70, 80 rooms. It's going to look at the readings, and then it's going to execute the mu star IT, and then the temperature will change to IT plus 1, and then it will execute the same policy again and again. Yes?
With what we were discussing before,
Yeah.
even though the mu's were allowed to be time varying,
Yes.
it seems like they could have been time invariant, right?
Exactly. That's what the result there is. That,
Okay, so we haven't changed
yeah,
anything.
yeah. So we started with a time varying because we didn't know, until now we didn't know if it has to be time varying or time invariant and so on and so forth. We didn't know about it, so we assumed that it is time varying. But it turns out that if I pick this as my policy and I pick this as my stationary policy, so I'm executing the same policy again and again, I get the same optimal V star, right? So if using this policy you achieve V star, then this is the optimal policy. Now, that is not to say that you can't construct an optimal policy that is time varying, but if you have a simpler solution, why to complicate our life, right? That's the argument. Yes?
What's an example of where you would need a time varying mu star?
So when do we need time varying mu star? Anyone wants to answer that question? Sorry? Non-stationary situation. So when the transition kernel is changing, Pij is changing, then you need to have a non-stationary optimal policy.
Or the cost.
Or if the cost is changing. Yeah, that's right. So there are two things that are stationary in this case, the transition kernel and cost. So if either of them change, then we have to change the policy. We have to make sure that we have a time varying policy. So that's why I was saying, when you think about the building energy system, the winter weather and the summer weather are two different transition, they have two different transition kernels, right? So therefore they have a time varying policy. So you have a summer policy and you have a winter policy, right? When does cost change? Why would the cost change? So remember that, all of our electricity bill, we have the same cost for electricity throughout the month, but not the commercial customer. So OSU is not seeing the same cost of electricity throughout the day. So every 15 minutes, the cost to OSU is changing. So right now, the electricity cost will be something, and in 3 minutes, the cost is going to change for OSU. Even though we are keeping all the lights on, the air conditioning is on, and all of that, everything is being done the way it is. But if you were a commercial customer, your cost will be changing every 15 minutes. Okay? So in those cases, the cost is changing, as a result of which your optimal policy would also change. Yes?
Your cost is changing every 15 minutes. Commercial customer, including OSU, the net temperature system, can't be a stationary policy because your cost is changing.
Yeah, so the question then becomes, do you really want it to be, do you want so that gets into the engineering systems part of it. So the startups who said that I'm going to change your policy every 15 minutes depending on what the cost is, those startups actually failed. And the reason is because nobody wants to tinker with their air conditioning system every 15 minutes. So sometimes what is optimal is not what is done on the ground because of other regulatory, legal, compliance, headache constraints that people might have or employees might have. So in fact, when I pitched this project to OSU, guess who actually blocked the project? The people who blocked the project were the cybersecurity people at OSU. So they said, you cannot tinker with our air conditioning system every 15 minutes because that's a cybersecurity risk on OSU buildings and we cannot take that risk. Okay, so just because something is optimal doesn't mean that it's going to be executed on the ground. Okay, that was 7-8 years ago. The person who blocked my project actually comes to my cybersecurity class. He takes a guest lecture in the cybersecurity class. So we are friends. We are friends, but he blocked my project. Any other question? Yes.
I was just thinking about we looked at the transition or the cost function would be time dependent.
That's right.
That would admit a time dependent optimal policy.
Yes.
And then you were talking about the air conditioning.
Yes.
And how that's an example of a.
It has both. It has a non-stationary transition kernel and non-stationary cost. Both of them are true.
Since the weather's kind of cyclical, can we embed the like date into the state space? Or?
That's a very good question. So remember when we were talking about the description of the state, and the state should be able to predict the cost and should be able to predict the predict itself at the next time step. So, and then we also said you want to pick the state space which is minimal in nature. You don't want to expand the state space too much, right? That was the first class when we discussed this. So you can push a lot of things in the state space, and at some point of time, everything will become stationary. So in the case of time of use cost, you don't have to look at the current cost, but you also have to put in the future cost that you are going to see. Right? Now imagine what the state space is going to look like. You have the current cost and the next 15 minutes cost and the next half an hour cost and so on and so forth. You've made the state very complicated in order to get stationarity. Now you have an optimal policy which is stationary because you have a stationary system. But guess what the complexity of this optimal policy is going to be? Pretty huge, because now you have state space is huge. And what's the complexity of computing this T operator going to be? Again, very huge, right? So you don't want to get into those situations. Any other question? These are all very good questions, by the way. Yes?
So in the case of the air conditioning,
Yes.
because the cost is changing every 15 minutes.
Yeah.
Like engineering assumptions and taking average cost of.
Yes. That's pretty much what people do. Yeah. Any other question? Okay, wonderful. So we are done with the discounted cost problem. So what did we do in the discounted cost problem? So we came up with this operator called the Bellman operator, right? We showed that the Bellman operator is contraction with the contraction coefficient alpha when the value function space is endowed with the sup norm or with the maximum norm, L infinity norm. In that case, T is a contraction. Consequently, this value iteration algorithm is going to converge to some steady state value function V bar. Turns out that that V bar is actually the optimal value function. So that V bar or V star, V bar is equal to V star, which is the minimum of the cost over all possible time dependent policies. From that V star, I computed my mu star and I set a stationary policy which is mu star. So at every point of time, I'm just using the same policy, mu star. So that's a stationary policy. And turns out that the cost using the stationary policy is actually exactly equal to V star. Consequently, mu star is the optimal solution. So there is a stationary policy which is optimal, right? So there could be non-stationary policy that is optimal, but why should we complicate our life? We'll just stick with the stationary policy because we know that it gives us the same expected cost. Now we'll do the same, we won't go through the same derivation, but I'll give you some hints about what happens in the average cost case and the stochastic shortest path problem. So let's talk about the stochastic shortest path problem or total cost problem. So any questions on this before I erase this stuff from the board? Okay. I'm going to keep the Bellman operator part here because we'll reuse this operator again and again. So this is the total cost problem. I guess I'm making another, not assumption, but so sometimes I'm going to let T go from 0 to infinity, sometimes it goes from 1 to infinity. So I apologize for making that confusion, for leading to that confusion. IT UT IT plus 1. So this is the total cost problem. What are the key features? So there exists a terminal state. Let me call this state terminal. So I have a terminal state and I'm going to name that state terminal. Then C terminal U J is equal to 0. So once you reach a terminal state, no matter what action and the next state you transition to, the cost is going to be 0. P terminal U is equal to 1 and P terminal J U equals to be 0. This holds for all U and for all J.
So the J is not terminal.
This J is not terminal, any other state. So once you reach the terminal state, you always transition to the terminal state and you can never transition to any other state. Yes?
Is it that like we don't know the terminal state at current periods, or do we know?
We know what the terminal state is going to look like. So if I want to go from here to my home becomes the terminal state. Okay? Or if I am treating a patient, the death turns out to be the terminal state of the patient. Okay? So once a patient dies, there is no cost of treatment. If the patient has died, the patient will remain dead with probability 1, and the patient cannot go back to some other state, a live state. So the probability of that is 0. Unless you are in zombie world.
And we always assume that each trajectory goes to the terminal.
That is going to be an assumption. I'll make that assumption shortly. Yeah. Okay. So I want to go from some initial condition. So I0 is given. This J mu is a function of I0, the initial state. And I pick a policy, mu, and I incur this particular cost. This policy could be a time varying policy or it could be a stationary policy. So far I'm not making any assumption on the stationarity of the policy. So I'm going to make an assumption. The assumption is as follows. So I'm going to first define proper policy. So mu is proper. So I'm going to assume that mu is stationary. So this is a stationary mu. Is proper if and only if there exists a not there exists probability that x n equals to terminal given any state I0 and ut equals to mu it for all t is greater than 0. And the assumptions is all stationary policies are proper. Here n is the size of the state space, so n is the cardinality of the state space S. Oh, yes, it should be IN. IN. Yeah, this is correct. So the state after n transition is terminal with positive probability under any policy, under the policy mu, then mu is proper. And the assumption is all stationary policies are proper. Yes.
So n is not
N there is time. But the time that I am picking here, n, is the same as the size of the state space. So if your state space is large, I expect this n to be large as well. By the way, this is not the only assumption, so there are different assumptions. Under different assumptions, there are different proofs. But the final algorithm is the same for all different assumptions. So this is just one set of assumptions under which the value iteration algorithm would converge. Yes?
Sorry, so just getting at the mu is proper if and only if you can reach the terminal state from any starting state in a reasonable amount of time.
In a reasonable amount of time, yes. That's exactly what, in simple words, mu is proper if no matter where you start from, as long as you keep executing mu, you reach the terminal state at time n with positive probability. Yes?
Is the IT on necessary since it's stationary?
This mu is a function of IT, yeah. So, right. So IT is a state, and so I have to pick an action based on the state, and mu is the policy which maps the state to action.
But it has to be a stationary policy.
It has to be stationary policy. So we are picking the same policy at every point of time. So what this result says is, say I want to go home, no matter what path, route I take, I'll reach my home eventually at some point of time. Right?
N is equal to the cardinality.
Cardinality of the set, yeah, of the state space. Okay? So if the state space is huge, then in that case, I'll reach the terminal state at a much later time step.
So
Okay.
it can be other integers as
Right.
well, right? I guess.
There are, sorry?
N can be, must be. The
Much bigger, yeah.
Must be. Oh.
Yeah. It could be very big, like depends on the situation, right? Yeah. Okay, so under this assumption, I'm going to have the same Bellman operator except that this alpha is going to be equal to 1. So same operator. But alpha is going to be equal to 1. So we are not discounting it, right? So alpha is equal to 1. So you use the same operator with alpha equals to 1, and you get a value iteration algorithm, and the result is Vk plus 1 equals to Tvk converges to V star, and mu star is optimal. So whatever mu star, you remember we had figured out a way to compute mu star from V star. Let me write it again. So mu star I is equal to argmin un ui of expected value of C plus V star. So this is how, there is no alpha here, so that's the only change. But with V star you can compute mu star, and that's the optimal solution in this particular case. And the proof is basically the same. This T is a contraction map, or T raised to n is a contraction map. And the norm on V is as follows. It's the weighted sup norm. So this is known as a weighted sup norm. So these weights, C, there is some way to compute C, and using those weights, those weighted sup norm, you can prove that T is a contraction map, or in T raised to n is a contraction map, and therefore it would converge to V star. There's a lot of stuff going on here, so that's why I'm not covering the proof in the class, but the same algorithm works in this case as well. The value iteration would work in this case as well. Any question? Yes.
So the convergence is the convergence in the specific norm you choose, right?
Yeah, exactly. So that's what, so some PhD student in 1970 spent his entire thesis figuring out what is the norm under which this T is a contraction. So I would imagine his or her PhD thesis would look something like this. Under this assumption and this norm, T is a contraction, and therefore it will converge to V star, and mu star is going to be optimal. So that's just one chapter of the PhD thesis. So somebody might have spent 1 year, 1.5 years figuring this thing out. Okay, and if you read these two books, Putterman and Bertseker's book, there is a whole bunch of assumptions under which the value iteration converges to the optimal solution, but we are not covering all of those different conditions. So to give you a flavor, some assumptions do not require all stationary policies are proper. They just require there is a proper policy which satisfies this condition for some m. So not necessarily n, but some m. So in those cases, you want the cost to go to infinity for certain trajectories. So there are all those different conditions under which this statement still holds. So read the book if you are interested in other possibilities for the total cost problems. Any other question? Okay. So I have 12 more minutes. So I guess I can talk about the average cost. Now, average cost is a bit complicated. Okay, so I'm not going to be able to cover the entire average cost case, but I'll tell you why it's complicated. So remember, in average cost, we are trying to optimize the steady state behavior. Now, is it obvious that all Markov decision processes will have steady state? Okay, so how many of you have taken control systems or dynamical systems? Okay, I'm assuming many people have taken. So remember, there is this notion of unstable system, right? Something that we all study in control systems. So there is something is unstable, which means that trajectories are going to infinity. Some trajectory is going to infinity. Okay, so unstable systems are not stable by definition, right? So similarly, in Markov chains or Markov decision processes, you could have systems that are unstable, and by unstable it means that they don't have a steady state behavior, or the steady state behavior is go to infinity or something like that, right? So very simple system where there is no steady state behavior. So you go from point 1 to point 2 and then go back to point 1 and then go to point 2 and then go back to point 1 and so on and so forth. There is no steady state behavior, right? You're going in a cycle. So that's a simple situation where there's no steady state behavior. There could be other complicated systems like an unstable. So I don't know if you've looked at this inverted pendulum example. So the pendulum goes down. That's the unstable part. So there are cases, there are policies. So remember that inverted pendulum is an example where you have some policies, some controller that keeps it inverted, and some other controller, which is typically the bad controller, that makes it non-inverted, right? So those are the cases where you have a bunch of policies that leads to a stable solution and a bunch of policies that leads to unstable solutions. So there are all these possibilities in a general system, general Markov chains or Markov decision processes. So therefore, when we talk about average cost case, we have to narrow down on the class of Markov decision problems that we are considering. So let me tell you about the communication structure. Of a Markov decision process. So I have a state S. I have a transition kernel P mu. So this S0, S2, S3, S4, right? So I have these 5 states, and from S0 I go to S1 with some probability, S3 with some probability. So I'll just put some random numbers, 4, 0.6. From S4 you go to S2 with probability 1. From S1 you go to S2 with probability 1. From S2 you go to S3 with probability 0.5. You go to S1 with probability 0.5, and so on and so forth. So this graph is known as the communication structure of the Markov chain or Markov decision process. So from this state, what all are the different states that you can transition to? So this graph encodes that information, and this is known as a communication structure of the Markov chain. Now you have various Markov chains where you have a bunch of transient states and then recurrent states. It's very easily depicted by a picture. So here is my initial point of the Markov chain, and I'm moving in some direction, and then I keep moving in some particular subset of the state space. So this is my state space S. So I start from some initial condition, and no matter where I am, where I start with, there is a bunch of states that I visit very often, and once I get within those bunch of states, I don't go out of it. Okay, so from here, from this region, I'm not going to go out of this region. Once I get into that region, I'll just stay within that region. So these states are known as recurrent states, because once you get into recurrent state, you remain within the recurrent states. You don't go out of it. And these are known as transient states. By transient state, what I mean is you can pass through that state maybe multiple times, but eventually you will go to the recurrent state. So in transient state, you're not going to spend infinite amount of time. In recurrent state, you can spend infinite amount of time. Any questions on this? So the communication structure allows you to figure out what the recurrent states are and what the transient states are. So can someone tell me what the recurrent states are? So if you look at it, there is no arrow that is going into S0, and there is no arrow that is going into S4. So if you start from S4 and S0, you end up going to S1, S2, and S3, right? So these are transient state. There is no arrow that is going into the transient state, and all the arrows going out of the transient state is going into the set of recurrent states. Once you go within this, once you go to either S1, S2, or S3, Actually, I need to go out of S3 also, so let me go out of S3 to S1. So once you go to one of these three states, S1, S2 and S3, then you keep circling within these three states, and those are the recurrent states. So if you think about economy, when we think about, let's say, tech companies, right? So we say that they become big and then they remain big. They never shrink. So that's the case where if you go beyond a certain scale, you get into a recurrent state and then you remain within that recurrent state. So some people will say this is an economy where rich continues to remain rich and poor continues to remain poor. So that's another case where you have two sets of recurrent state. One set of recurrent state is rich, another set of recurrent state is poor. And once you get into one of those recurrent states, you remain within those recurrent states. Okay, so if you have one set of recurrent state and another set of recurrent state and a bunch of transient states, then this is known as a multi-class Markov chain, because you have two classes that are recurrent and then you have rest of it which is transient. If you have only one set of recurrent states, then it's called a uni-chain. Okay, so it's not multi-chain, it's uni-chain. So let me write it here. You could have uni-chain, one set of recurrent states. You have multi-chain, two plus two or two more than two sets of recurrent states. Okay, so you could have uni-chain, you could have multi-chain, and then you could have unstable chains where things are going off to infinity. So there are lots of possibilities. So in the next class, I'll talk about the value iteration algorithm for uni-chain class of Markov decision processes, and then I'll comment on how do you compute solutions to multi-chain. Okay, so we'll talk about two different ways of computing solutions to average cost problems, and that'll be done in the next class. So thank you so much. If there are any questions, I'll be happy to answer it after the class.